This is one of a series of lectures produced by FMSP for revision of modules. This one is looking at the Edexcel FP1 specification and in particular matrix algebra. The matrix algebra specification first of all looks at addition, subtraction, multiplication of matrices. That I'm going to take as read, other than to remind you that when you're multiplying matrices, then the order of the matrices is important, so that the number of elements in the row of the first matrix must correspond to the number of elements in the column of the second matrix. So that we talk about the number of rows by column, so this might be an n by m matrix. Then the second one must be an m by something matrix, so m by p. Then as long as that is true, it will produce a matrix which is of order n by p. The other thing I will say about products of matrices right there is to remember that the idea of matrices A, B is not necessarily equal to B, A, so that the order in which you write the and actually perform the multiplication is very, very important. Determinants of matrix, you need to know that for a matrix A, B, C, D, so if this is my matrix, then its determinant, either written as det m or mod m, is equal to AD minus BC. So it's the diagonals multiplied together and then subtracted. And once you've got that, then the idea of singular and non-singular. Singular matrix is one where the determinant is equal to 0. So singular det A is equal to 0, and non-singular otherwise. In other words, it is not equal to 0. Now, as long as it's a non-singular matrix, then the inverse of matrix M inverse, is given by, well, we take 1 over the determinant of M, and the matrix is produced by swapping the leading diagonal so that it will become D and A. This is what's referred to as the leading diagonal. Swap the leading diagonal and then change the sign of the other diagonal. The other thing about the determinant is when we're looking at transformations, then the determinant is equal to the area scale factor, and this sometimes comes into questions. The area scale factor of a particular transformation is equal to det m. The second part of the specification is about using matrices to represent transformations, so that, or at least to perform transformations. The first bit simply reminds us that AB, the notation AB, means that the first transformation is B, and then it's followed by the second transformation A. This is very similar to functions, of course, where you have fg of x is the function g applied to x, followed by f being applied to the result of that. After that, you need to be aware of a series of matrices for particular transformations. Now, these are, first of all, what are called the isometries, reflections and rotations. The specification is particular in that it talks about rotations and reflections with angles looking at 45 degrees. So the lines that we're going to be talking about are the axes, or the lines y equals x and y equals negative x for the reflections, and the rotations by multiples positive or negative of 45 degrees about the origin. All of the particular transformations can be found by considering the unit vectors I, which is the vector 1, 0, and j, the vector 0, 1, and what happens to them when we perform a particular transformation. So for example, a rotation of 90 degrees about the origin would produce the following set of unit vectors. I dashed would be here at 0, 1, and j dashed would be here at negative 1, 0, so that the matrix for that rotation of 90 degrees anti-clockwise, so positive 90 degrees, is 0, 1, negative 1, and 0. The reflections, again in 45 degrees, so and the axes also are quite straightforward to work out using this idea. It's worth pointing out that the determinant of a matrix, being the area scale factor, if the determinant is equal to +1, then this is going to be a rotation. And it's one way of checking that you've actually got the correct matrix. If it's equal to -1, then it will be a reflection. This also goes for positive and negative other numbers, but when they're then combined with the enlargement. So that it's we've already discussed that the determinant is equal to plus or minus k. We've got an enlargement taking place. The formula sheet does have the following information, and you can use these, but as I said already, for FP1 we're looking at multiples of 45 degrees, so that the most of the matrices can be easier to work out using that idea of the unit vectors. However, you can use 45 degrees substituted, or multiples of that substituted into these matrices to give you the correct expressions. Going on then now to look at some particular questions. First of all, a straightforward one looking at multiplication of matrices. So A, B, remember that that order is important. 5, 3 multiplied by -3, 5, -1, 2. The answer to this is quite straightforward, so it's just a matter of making sure that you get the multiplication. The 2 multiplied by 3, 0 times 5, giving you 6. 2 multiplied by -1, and 0 multiplied by 2, giving you -2. And then sorry, beg your pardon, I've written that in there incorrectly, haven't I? So just correcting that error, that should be -3 in there. So 2 multiplied by -3 is -6, beg your pardon. And then we have 5 multiplied by -3 and 3 multiplied by 5, so they cancel out to give you 0. And -5 plus 3 times 2, 6, gives us +1. The 3 marks for that particular question, they're given as a method mark, so that's indicated by getting at least one of these correct. You get an accuracy mark if you get 3 correct, and then a second accuracy mark if you've got all 4 correct. So the method mark accuracy and accuracy. Just giving you 3 marks there. The second part of the question goes on to look at this idea of the unit vectors. So this one here, we've got I dashed is at -1, 0, so this is I dashed. And j dashed is at 0, 1. So j hasn't actually moved. So therefore we've got a reflection, haven't we? The transformation is a reflection in the y-axis, or the line x equal to 0. Remember what I said about the determinant. It's worth checking that this is definitely a reflection. If you look at det C, so just a note here, it's not part of what you're asked to do, but just a note that the determinant of C is equal to -1, and that indeed then tells you that this is going to be a reflection. Well, of course, if it's a reflection, then the last part of the question, it's just that idea that if you perform a reflection twice, you get the identity matrix, so that I can write down that C squared must be equal to 1, 0, 0, 1, the identity, and of course C100 must be equal to C squared to the power 50. It is only a write down, so you don't need this explanation, so that the answer is also the identity matrix. The marks, by the way, for the part B of that, the marks are allocated as a method mark for seeing that it's a reflection, and then an accuracy mark for getting that complete statement. It's a reflection in the y-axis. And then this here is just a single mark, so it's a B1 mark. There's no method needed there. It is simply a statement of that answer. Okay, the second question here starts off with, again, statements of just writing down. So just knowledge of an enlargement being given by 0 and 8, so 8008. And then the reflection in the x-axis, so we had the reflection in the y-axis in the last question. This time it's the I vector which stays the same, j vector which becomes equal to 0, -1. So the reflection in the x-axis is given by 1, 0, 0, -1. So there the I is the invariant vector this time. Goes on to say, hence or otherwise, find the matrix T represents an enlargement with this particular enlargement, followed by a reflection in the x-axis. So we've got the enlargement 8008 followed by, so we're going to multiply that on the left. This is the second transformation here. And that becomes equal to 8, 0, 0, -8. So the first 3 parts quite straightforward. I'll look at the marking of that before I go on. These are simply statements, write down, so they're B marks, B1 and B1 here. And then there's a method mark, M1, and accuracy mark A1. So the method mark here for the matrix multiplication in the correct order. I'm going to go on now and look at the final part of the question on a new page where I've got a little bit more room. So here we are then, first of all finding AB. So this is just a case of writing down AB, 6142 multiplied by, we've got some algebra in here, K1, C, and negative sixth. The multiplication is straightforward, algebraic of course, so we get 6k plus c, and then in the second element on the first row we've got 6, and then negative 6 or minus 6, giving us 0 as that element in the first row, beg your pardon. And then the second row, 4k plus 2c, and 4 minus 12, giving you minus 8. So that's the finding AB. Given that AB represents the same transformation as T, the one that we had before, so we're given that this is equal to that matrix before, which was 8, 0, 0, and negative 8. So this is simply a way of getting you to realize that we can write down a pair of simultaneous equations. If these are going to be the same, then the elements in each entry must be the same, so that 6k plus c must be equal to 8, and the other entry is 4k plus 2c must be 0. Well, these are simultaneous equations which you can solve in many different ways, of course, by adding, subtracting, or multiplying. Perhaps the easiest way here is to see that from the second equation that c is equal to negative 2k, c is equal to negative 2k, and then substituting that into the first equation gives us that 4k is equal to 8, and therefore k equals 2 and c is equal to negative 4. The marking here is again relatively straightforward. There are method for writing the matrices correctly and showing at least one term being correctly done, and then an A1 mark if we're getting 3 terms, and a second A1 mark for the fully correct multiplication. And the final part is marked as a method mark for realizing that simultaneous equations are required, and then an accuracy mark right at the end for that final answer. The final question I want to look at then is this one, and it starts off in a similar sort of way, just getting you to do some simple things with the matrix that you're given, and then looks at using the transformation and brings in the idea of the area scale factor. So I'm going to do this in 2 parts. First of all, the first 2 parts. The determinant of A, simple statement, we're multiplying together the leading diagonal and subtracting from it the other diagonal multiplied together. So I'll write out, you don't need to write it out fully, but it's 2 multiplied by 3 and then minus negative 1 multiplied by negative 2. So that gives you a determinant equal to 4. The inverse of A, then the method is to take the leading diagonal of A, 2, 3, and swap it, and change the sign on the other diagonal, so 1 and 2 in that fashion, and then divide by the determinant. And that's it for that one there. The marking there is B1 for the first determinant there. You either get it right or you don't. The second part of the question is marked as a method mark for manipulating the matrix there, and then an accuracy mark, the A1. So note that you can only get that second accuracy mark if your determinant is correct. So it's not going to be a follow-through mark there. Okay, going on to that then, we'll look at the second part of the question on the next page, where there's a little bit more room. The part C of this question is referring to this situation where we've actually taken a triangle, an unnamed triangle, and transformed it to a new triangle by using matrix A. So we've gone from R and we've produced S by multiplication by the matrix A. And we're told that the area of S is 72 square units. So remember then that the multiplication, the scale factor for this enlargement, is the determinant of the matrix. So the area of S is going to be 4 times the area of R. So that area of R is the determinant, 4 times area, I beg your pardon, area of S is the determinant of R multiplied by the determinant 4. Well, we're told in the question that S is 72, so therefore the area of R is equal to 72 divided by 4, or 18 square units. The question then goes on and gives us the coordinates of S and asks us to find the coordinates of the vertices of R. Now, of course, we went from R to S using A, so to come back from S to R, we've got to use A inverse. So we can do that, and we simply take what they're expecting you to realize is that the coordinates of R will be given by A inverse times a matrix for S. So that we need to take the inverse, which we'd calculated before as being 1/4 of 3, 2, 2, 2, and multiplying that by the matrix for the vertices. These are done as columns, so 0, 4, 8, 16, and 12, 4. So this is A inverse multiplied by S will be equal to R. Well, it's easier to leave the quarter until the end, so it's just a case of multiplying through then this first row by each of these columns in turn. I'm sure you can do that to give you 8, and then so I just realised there's a slight mistake in that matrix there, that it's 8, 16, not 8, 6. So that the second entry here, 3 multiplied by 8, and then 2 times 16 gives us 56. (44), and then taking the second row, we get 8, 40, and 20. And then we can look at dividing everything by 4, so that we get 2, 2, 14, 10, 11, and 5. So that the vertices of the points are given by 2, 2, 1410 and 11.5. Okay, the marking there in that section then, the first part where we're looking at the area is just an M1, S1. The part D, then a little bit more involved in this. The first one is a method mark, simply for attempting to use A inverse. So this is a method mark here, M1. Then the accuracy marks come in the matrix right at the end. There's A1 if one column is correct, another A1 if two are correct. And then the final one is for relating that to vertices, so you must be giving coordinates, because the question is very specific. It doesn't ask for the matrix for R, it asks for the vertices. So the vertices of R written as coordinates, all three of them correct, gives you the final accuracy marks. Okay, that's the end of this session, a revision session for FP1. There are others available for this and other units for all the courses at Edexcel and other boards.